Welcome to lecture 6 of moving charges and magnetism. So we are beginning with a problem. So it is stating a uniform magnetic field of 3000 Gauss is established along the positive Z direction. A rectangular loop of side 10 cm and 5 cm carries a current of 12 ampere. What is the torque on the loop in the different cases shown in the figure? What is the force on each case? So this is the problem which is referring, and these are the three diagrams associated with it. So let us begin with the first one. So when we are beginning with the first one, so I am redrawing the diagram back again. So if I redraw this arrangement, so this arrangement is looking like this. So this is referred as y-axis, this one is x-axis, and this one is z-axis, and the coil is in this direction, carrying current like this. The direction of magnetic field is in the upward direction, the vector. So for any case which we are going to solve, a portion of calculation remains the same. So I am doing that calculation first of all, which will remain the same for any case which we solve. So the first thing which we write over here is the strength of magnetic field, which is given to us as 3000 Gauss. So the strength of magnetic field is given to us as 3000 Gauss. We convert it into Tesla and we attain a value equal to 0.3 Tesla. The area of rectangular loop is going to remain the same in each case. So it is 10 centimeter into 5 centimeter. So if we will convert it into meter square, so we will attain a value equal to 5 into 10 to the power of minus 3 meter square. Now if I write the magnitude of magnetic moment, which is equal to INA, so I am only writing the magnitude because the direction of magnetic moment will change in each case. So the value of magnetic moment is equal to current is equal to 12, number of turn is 1, and area is 5 into 10 to the power minus 3. So the magnitude is equal to 0.06 ampere meter square. So these parameters which we have written over here will remain unchanged for all the three cases which we are going to solve. Now in the first case over here, the direction of magnetic moment can be determined using right hand rule, and if we do so, so we are observing that the direction of magnetic moment is along the positive x-axis direction. So if we curl our right hand in the direction of current, so that the thumb will be pointing outside the screen, that is in the positive x-axis direction, and hence I can write that the value of magnetic moment is equal to 0.06 ampere meter square in the positive I cap direction. The value of magnetic field B vector is in the upward, that is the z axis direction. So we are writing it as 0.3 Tesla K cap. So if we write the magnitude of torque which it is going to experience, or the along with it direction, so the value of torque vector can be written as m cross b. So if we do cross product of m and b, so we attain a value equivalent to minus 0.018 Newton meter J cap. So the direction is in the negative y axis, that is in the negative J cap direction, with a magnitude of 0.018 Newton meter. The net force for the loop placed in the uniform magnetic field is 0. So the value of the force in each of the three cases will be 0. So I will not be answering it back again. So the value of force on a loop placed in a uniform magnetic field, the net force is always 0. So we are not answering it for the next two cases. So let us deal with the other case which is being asked. So I am drawing case B. So let us come to case B. So in case B, the loop is placed like this. So if the loop is placed in this fashion, this one is y axis, this one is x axis, and this one is z axis. So the value of magnetic field is in the upward direction. So nothing is going to change in this case. There is no change at all. If you check the direction of magnetic moment, we have only placed the loop with its length behaving like a breadth and breadth behaving like length. So that is the only difference between case A and case B. So if we calculate the value of m vector, that is magnetic moment vector, the direction is still in the positive x-axis direction, that is outside the plane of the screen, and the value is going to remain 0.06 ampere meter square I cap. So there is no change or no difference between A and B. So the magnitude of torque with its direction remains unaltered. The value remains unaltered. So now we are coming to the third case. So if we consider the third case, so in this particular case, if we draw the three axes, that is x, y and z respectively, so the loop which we are discussing about is in the xz plane. So the loop is in the xz plane with the direction of current as shown. So this is the direction of current. So now if in this case, if we use our right hand rule, so the loop is in xz plane, so the value of magnetic moment will be in the negative y-axis direction. When I say negative y-axis direction, so I mean to say that the value of m vector will become negative of j cap. So this is the change in the value of m vector in this particular case. The magnitude of m remains the same, the magnitude of magnetic field remains the same, the direction of magnetic field remains the same. Magnetic field is still in the upward direction along the z axis, so it is remaining the same. And if we perform m cross b this time, if we perform m cross b this time, so if we calculate m cross b, so the value of m is equal to minus 0.06 j cap cross of 0.3 Tesla k cap. So the value is going to be minus 0.018 Newton meter in the negative x-axis direction, that is minus I cap. So the magnitude is equal to 0.018 Newton meter in the negative x-axis direction. So now we are going to begin with the next topic. So we are beginning with the magnetic dipole moment of a revolving electron. So we are discussing the magnetic dipole moment of revolving electron. So if we consider this, so we are basically consider that electron is moving with a constant speed v along a circular path of radius r around a nucleus, and we will be calculating the equivalent value of current through its path, the strength of magnetic moment, and then we will also try to establish a relation between the angular momentum and the magnetic moment of the electron. So I am considering something like this, that there is a centrally located nucleus having charge plus Ze, and the electron is moving in a circular path at a distance r in this direction. So this is the electron, and the speed of the electron is given as v. So if we consider a point P on the path of the electron, so I can say in one revolution of the electron a charge of E crosses the point P, and hence if we use this expression that current is equal to charge flown by time taken, so we can calculate the equivalent value of current due to the electron flow or due to the motion of electron in an atom. So the value is calculated as E upon the time is written as 2 pi r by V. So the value of equivalent current due to the motion of electron is equal to EV upon 2 pi r. Now the next parameter which we are discussing is that the area enclosed by the circular current. So the area enclosed by the circular current is equal to pi r square, and hence I can say that the value of magnetic moment m, so if we calculate the magnitude of magnetic moment, which is equal to INA, so this can be written as EV upon 2 pi r multiplied by area, that is pi r square. So we attain a value equal to EVR by 2. So this is the magnitude of magnetic moment because of the flow of electron in an atom, and the direction of this magnetic moment is in the direction perpendicular to the loop. So the direction of this magnetic moment is in the direction perpendicular to the loop. So if we can write the angular momentum because of the motion of electron, so if we write the magnitude of angular momentum because of the motion of electron, then it will be written as mvr. So the value of angular momentum will be written as mvr, and if we calculate the ratio between the magnetic moment and the angular momentum of the revolving electron, so we will attain a value like this: EVR by 2 into MVR. So the value is equal to E upon 2m. So the charge of the electron divided by 2m, this is going to be the value of the ratio between the magnitude of magnetic moment and the magnitude of angular momentum for a revolving electron. So now we are beginning with the last portion of this chapter, that is studying a moving coil galvanometer. So we will divide this topic into two parts. So in the first part I am going to discuss about the working or making of a galvanometer, and then in the second part we will be discussing about how we are going to convert a galvanometer into a voltmeter and an ammeter. So the first thing first, so if the question is asked what is a galvanometer, so we define it in this way: a galvanometer is a device. A galvanometer is a device that allows very feeble current, very feeble current to pass through them. So it allows a very feeble current to pass through them. And if I draw a arrangement as to how the inside of a galvanometer looks like, so I am drawing it in two different views. So I am first of all showing you the top view of the moving coil galvanometer. So in this top view we are drawing it in this way, that there is a north pole and a south pole responsible for the uniform radial magnetic field that is generated inside the galvanometer with a central soft iron core having a large number of turns of wire. So it is having a large number of turns of wire, and over here there is a pivot point associated with a helical spring, and a pointer points out somewhat like this onto a scale fitted in the galvanometer. So this is the measuring scale which we have with a helical spring and a large number of current carrying wire associated with this soft iron armature coil. So now what is exactly going to happen is, because of the north and south poles, a uniform radial magnetic field is generated. When I say a uniform radial magnetic field is generated, radial magnetic field is generated, I mean to say that the value of torque vector, which will be written as mb sine theta, so over here the theta is equal to 90 degree and the value of torque is equal to mb. Now it is because of this torque that the pointer which is attached with the soft iron core will move and point to a particular number on the scale. That is, this torque is responsible for the production of magnetic moment and is also responsible for the motion of this armature coil and hence the motion of the pointer associated with it. So if I write the value of this torque, so I can write that the magnetic moment is equal to INA and the value of magnetic field is B. So the magnitude of torque is equal to INAB. So this is the value which we are going to attain for this particular problem or this particular part, that is equal to INAB. Now the spring which I was talking about will provide a counter torque which will balance the magnetic torque, which is equal to INAB, resulting in the steady angular deflection of the pointer. So I am writing it in this way, that we are considering that K is the torsional constant of spring. K is the torsional constant of spring, and we are considering that it is undergoing a deflection phi. So phi is the deflection angle. So I can say that this torque provides a counter torque K phi, which will balance the magnetic torque INAB. So this is going to balance the magnetic torque INAB, and from here I can say that the deflection can be indicated as INAB by K, or in this expression I can say that phi is equal to NAB by K into I. So this entire parameter NAB by K is a constant. It is a constant and it is regarded as a galvanometer constant. So we say that this entire thing is a constant because the number of turns associated with the galvanometer coil, the area of the armature coil, and the torsional constant of the spring. So all these parameters are not going to change under any circumstance as to whatever is happening in the galvanometer. So I say that this entire parameter is a constant. So this entire parameter is regarded as a galvanometer constant, or I can say that the deflection produced is directly proportional to the current that is flowing in the galvanometer coil, and this parameter is regarded as a galvanometer constant, which I can write from here that I is equal to K upon NAB into theta, where K upon NAB is called as galvanometer constant. So this parameter K upon NAB is regarded as galvanometer constant. So now the first term that we define associated with it is sensitivity. So when I say sensitivity, I mean to say the current sensitivity. So the deflection produced in the galvanometer coil per unit flow of current is regarded as its sensitivity. So theta by I or phi by I can be written as NAB by K. So this is regarded as the sensitivity. For the large sensitivity, we can say that the magnetic field B must be large. There must be a presence of a soft iron core which will increase the magnetic field. The number of turns must be large and the value of torsional constant must be small. So if we consider this aspect, so I can say that in order to increase the sensitivity of the galvanometer, so we say that the number of turns in the galvanometer coil must be large, the area of the armature coil must be large, the strength of the magnetic field must be large, or a soft iron magnetic core must be introduced to intensify the magnetic field, and the torsional constant of the spring attached for this operation must be small. So all these parameters will increase the sensitivity of the galvanometer, and this is also regarded as current sensitivity. This is regarded as current sensitivity. So just like current sensitivity, I can involve a voltage sensitivity. That is, we defined current sensitivity as the deflection produced in the galvanometer coil when a unit current is passed through it. So if I were to define a term called as voltage sensitivity, so I would have defined it as the deflection produced in the galvanometer coil when a per unit voltage difference is provided across its end. So when a per unit voltage difference is provided across its end, then the sensitivity is regarded as voltage sensitivity. So I am converting this expression which we attained. So I am writing from phi by I, we had the value written as NAB by K. So if I make this term like this, if I multiply it by resistance on both ends, so if I divide with resistance in denominator in both ends, so this parameter will become phi by V, which is equal to NAB by K into 1 by R. So we attain a value equal to this, and this R is a very large resistance that is connected in series with the galvanometer. This resistance R is a very large resistance which is connected in series with the galvanometer. When the conversion of galvanometer into a voltmeter is performed, we will discuss about it soon. So this term is regarded as voltage sensitivity. This is regarded as voltage sensitivity. So now we are beginning with conversion of galvanometer into a voltmeter and ammeter. Conversion of galvanometer. So in the first part we are dealing with into an ammeter. So for a galvanometer, we have learnt that a galvanometer is a device that allows very feeble current to pass through it. So if I draw this galvanometer like this, that this is the arrangement of the galvanometer, and this is the resistance which is offered by the galvanometer. So I am marking this as the positive terminal and this as the negative terminal, and a very feeble current that is passing through it is represented as Ig, and the resistance of the galvanometer is equal to Rg, as a result of which a deflection is produced. So if I write the potential difference between the 2 points, which I am referring as A and B over here, so I can say that the potential difference VA minus VB is equal to IGRG, and Ig is the very feeble current which the galvanometer will allow to pass through it, usually of the order of microampere. So in this case, if we wish to convert this galvanometer into a device which can measure a larger current, maybe of the order of milliampere or at least ampere, so what are going to be done? So in order to convert this galvanometer into an ammeter, so first of all let us understand what an ammeter is. So it is a device that measures current flowing through it, that measures current flowing through it. So in order to convert a galvanometer into an ammeter, in order to convert galvanometer into an ammeter, a very small shunt resistance is connected across it. So when I say shunt resistance, I mean to say a resistance in parallel. But it must be kept in mind that the ammeter as a device is connected in series with the circuit. Ammeter is connected in series with the circuit. Is connected in series with the circuit. But in order to convert a galvanometer into an ammeter, we are attaching a shunt resistance. When I say I am attaching a shunt resistance, I mean to say something like this, that in this arrangement, I will attach a smaller resistance through which the majority of the current will bypass and a very small current will continue to flow through the galvanometer. So I am referring it as shunt resistance S. So now what is going to happen if suppose I current enters this entire network of galvanometer. This one is the positive terminal, this one is the negative terminal. So over here the current will bypass. So Ig current will pass through the galvanometer, which is the feeble current, and the rest of the current, that is I minus Ig, will pass through the shunt resistance. So this will pass through the shunt resistance, and over here they will combine back again to become I, and this is regarded as Rg, or the resistance offered by galvanometer. So if I write the value of potential difference, so this time I can write it in two ways, that is Ig Rg, which was originally written, and it is equal to I minus Ig times of shunt resistance S. So if we wish to calculate the value of shunt resistance which must be connected, then we can write it as Ig Rg by I minus Ig. So this is the value of shunt resistance which must be connected to make the range of the galvanometer equivalent to I. Now we shall discuss about the conversion of the galvanometer into a voltmeter. So we are discussing B part, into a voltmeter. So if we consider this, I am once again drawing the basic arrangement of the galvanometer. So in this basic arrangement, this was the galvanometer reading coil and the resistance which it is offering, that is Rg, point A and B, which is the positive and the negative terminal marked on the galvanometer, and a feeble current Ig that was passing through it. So now in order to make the galvanometer into a voltmeter, the first thing which I am writing over here is that a voltmeter is a device that measures potential difference across 2 points in a circuit. The next fact, in order to convert a galvanometer into a voltmeter, in order to convert a galvanometer into a voltmeter, a large resistance is attached in series with it. A large resistance is attached in series with it. But the device voltmeter is connected in parallel with an electric circuit. So if I were to convert this arrangement into a voltmeter, so with this arrangement, I am attaching a very large resistance associated with it, and this entire device will now behave like a voltmeter and will allow the feeble current to pass through it. This is Rg and this is suppose X. So now I can say that the potential difference that it can measure is equal to Ig Rg plus X. Now the points that must be kept in mind is, ideally an ammeter is considered as a device that offers zero resistance, and ideally a voltmeter is considered as a device that offers infinite resistance. And that is the reason when we draw an electric circuit, till now whenever we have drawn an electric circuit, so if I consider that electric circuit like this, where there is a DC source attached with a key K, so we consider that all the current that will start flowing through the battery will enter this voltmeter, and then there is a resistance through which the potential difference is to be measured, and a rheostat attached over here, and this is the complete circuit that we are talking about. This is key K, ammeter A, resistance R, a voltmeter V, and a rheostat RH. So whenever we have considered about a circuit like this, we have considered that all the current that is passing through this passes like this. So till now we haven't never considered that the current branches when it is flowing through this resistance R. There is no current that is branched into the voltmeter, because we are considering that ideally ammeter offers zero resistance and voltmeter offers infinite resistance. Infinite resistance. And the arrangement which we learnt is inside this box. So all the arrangement which we have learned is performed inside this box of ammeter and inside this box of voltmeter. That is, I mean to say that if I draw a bigger circuit, let me draw a bigger circuit for the better understanding. So I mean to say something like this, that there is a source of current, a key attached, and then it comes here. So over here inside this voltmeter, this is the arrangement which I am talking about. So this is what we have read till now. So this is rheostat RH, and when we see the voltmeter, when we see the ammeter, we represent this as a single circle like this. That is, this is ammeter. So inside this ammeter, this is Rg, and this is shunt resistance S, and this one is the external resistance R, and this is the box which is commonly regarded as voltmeter, which we write in circuit as V, where this is the large resistance that is attached, which we call as X, and this is the resistance of galvanometer Rg. So I think this will give you the clear picture as to how the inside of a galvanometer looks like. Let us deal with a problem. So it is stating a galvanometer coil has a resistance of 12 ohm and the meter shows full scale deflection for a current of 3 milliampere. The question is asking, how will you convert the meter into a voltmeter of range 0 to 18 volt? So if we consider this problem, so it is stating that the resistance of galvanometer coil, that is Rg, is equal to 12 ohm, and the feeble current that is passing through the galvanometer, that is Ig, is equal to 3 milliampere, which we write it as 3 into 10 to the power of minus 3 ampere. Now the requirement is that the voltmeter should read up to 18 volt. So we are considering that a large resistance capital R is attached. So the effective resistance of the circuit now, the effective resistance of galvanometer now will become R plus 12 ohm. And on passing this feeble current, that is 3 milliampere, the potential difference must be 18 volt. So over here I can write that V, that is equal to 18 volt, is equal to R plus 12 into feeble current, that is Ig. So if we solve this out, we write it as 18 upon 3 into 10 to the power minus 3 is equal to R plus 12. So we have 6000 minus 12 is equal to capital R, where capital R will come out to be 5988 ohm. So this is the resistance or the external resistance that must be connected along with the galvanometer to convert it into the voltmeter of the required range. Let us deal with one more problem. A galvanometer coil has a resistance of 15 ohm and the meter shows full scale deflection for a current of 4 milliampere. How will you convert the meter into an ammeter of range 0 to 6 ampere? So in this case, the question is referring that the resistance offered by galvanometer is equal to 15 ohm, and the galvanometer current Ig is equal to 4 milliampere, that is 4 into 10 to the power minus 3 ampere. The requirement is to allow a current of 6 ampere up to 6 ampere to flow through it. So I can say that this arrangement must look like this. So there will be a arrangement like this, and we are connecting a shunt resistance across it. So over here we are calculating for this shunt resistance. so that this feeble current Ig will pass through the galvanometer when an input of 6 ampere is given. So the remaining value, that is 6 minus Ig, must pass through the shunt resistance. So if we solve this problem, then I can write it as that 6 minus Ig, that is 4 into 10 to the power minus 3 multiplied by shunt resistance, is equal to Ig, that is 4 into 10 to the power minus 3 into resistance offered by galvanometer 15. So from here we can calculate the shunt resistance as 4 into 10 to the power minus 3 by 15 upon 6 minus 4 into 10 to the power minus 3. So we can ignore this part, that is when we say 6 minus 0.004, we may ignore this part, and the value that we obtain over here is equal to 10 milliohm. So 10 milliohm shunt resistance, which is a smaller resistance, must be connected in parallel or in shunt with the galvanometer to convert it into the ammeter of the required range.